This is a look at energy in rotational motion. Rotational kinetic energy, the formula for it's kind of derived the same way that I is. So you have a bunch of GMs going around and you have a rotating object. In each DM, each part of the mass is a distance of r away. So the total kinetic energy is the sum of dm v squared times r. And when you add up all the dm's, you get 1/2 I omega squared. Something important to know when you have a question about where something's rolling is knowing when it's rolling without slipping. Now, that's the case most of the time. In AP Physics, most questions are going to say you have rolling without slipping. When you're rolling without slipping, then this is true. V is r omega. That means that all the rotational motion is converted into linear motion. So here's a question about rolling without slipping. You have a horizontal force being applied to a ball, a distance of d from the center. The ball has a radius of r and a mass of m. It's a solid sphere, so I is 2/5 mr squared. And you have the force applied d away. Determine d as a fraction of r, such that it rolls without slipping. So this is a case where something is rolling, so it's both having linear motion and rotational motion, so we can use both torque equals I alpha and F equals ma. And those are the two equations there. So for torque equals I alpha, torque is force times distance. So there's force times distance equals I, which is 2/5 mr squared times alpha. And then that has to be true to roll without slipping. So we had V is r omega, but also if you're rolling without slipping, then A is alpha times r. So what I did there, I replaced alpha in the equation with A over r, and then brought ma in here, because this is true for linear motion, that's the only equation for linear motion. I brought ma in for F, and then I got to here. So Fd, which is the torque, MAD, equals 2/5 mr squared A over alpha, and then you solve that for the ratio d over r. And you get that d is 2/5 r. Example B is a pretty typical Pulley question for rotation. This is a question, it should say that there's no slipping of the string on the pulley. So that means as the string pulls the pulley down, the pulley is going to spin V equals r omega with the pulley. Okay, and this is a case again where we have rotational motion of the pulley and linear motion of the block. So we're going to do F equals ma torque equals I alpha. But first, this is a question with forces, so we're going to do a free body diagram here. So we'll start with the pulley. The pulley only has one force on it, and that's tension in the rope, and that's going down. And the pulley is rotating. It's not moving linearly, so we're going to use torque equals I alpha for the pulley. And then here's the block. Remember, in physics, the direction of motion is positive, so mg is my downward direction, that's the positive force. And then here, tension is negative, because it's against the motion. This is the case where we're going to use F equals ma, because this is linear motion. So we have torque equals I alpha and F equals ma. For the pulley, the torque is the force times the distance. So the force is applied a distance of r away. Here's my tension force. It's applied a distance of r away from the pivot. And then I, this is a solid wheel. I for a solid wheel is 1/2 mr squared times alpha. And then for F equals ma, mg is our positive force. That's in the direction of motion because it's moving down. And then torque's negative. Now we just got to merge these two equations together. And again, since we have rolling without slipping, we're going to have that alpha is A over r. Now we can merge these two equations together. Okay. So when you simplify this, the r's cancel out, you get t is 1/2 ma, and you can bring this in here and plug it in for t. And there's your answer. Example C looks at when does a force cause a torque. So this is a case where a cannon is fired, or a cannonball is fired horizontally out of a cannon. It leaves the cannon with a linear speed v and an angular speed, because it's rotating, of omega. And the question asks, how does the linear velocity change in flight, and how does the angular velocity change in flight? Part A is easy. It's going to go down. The cannonball is going to slowly go down because there's a force of gravity. So it'll have a constant x velocity, but an increasing y velocity, so it's going to increase in speed. Now for angular speed, think about the ball here. It's going to rotate about its center of mass. The force of gravity acts at the center of mass. So its angular velocity is going to be constant because there's no torques here. Okay, And gravity does not cause a torque because it acts at the center of mass. So it does not cause a torque about the center of mass. All right, total kinetic energy, this is where you have something rolling across the ground. This is just saying you have 1 Fi omega squared because it's rotating. Now it's also going to be linearly, so you have 1 FMB squared. We're going to look at a question now where something is rolling. This is going to be a classic, something rolling down an incline. So this is a common type of question to see on the AP Exam FRQ section. This is a thing rolling down an incline without slipping. This one is a hollow ball, so I is 2/3 mr squared, where m is the mass of the ball, r is the radius, the incline has a height of h, and also given is the angle theta, the incline makes with the horizontal. So there's a couple of questions here. The first one is to find the linear speed of the ball when it reaches the bottom of the incline. So as the ball rolls down the hill, we're going to use conservation of energy here. It starts off at the top of the hill with potential energy, and it turns it into kinetic energy. And that's going to be linear and rotational kinetic energy. What's going to make this go slower than something that slides without friction? That's a common question to be asked as well. If something slides without friction downhill, it's going to convert all its potential energy into just linear kinetic energy, and it's going to go faster. If it has to rotate, then it has to convert its energy into both linear kinetic energy and then rotational kinetic energy. So it's rotating, that's additional kinetic energy that it has to gain. There's a little note there. So something that slides without friction will slide down faster than something that rolls without slipping. That's a common thing to be asked. So to solve this, we're going to use conservation of energy here. So a very important first step in any AP question like this is to write down conservation of energy, because you usually get points for saying, hey, I know that I'm using conservation of energy here. And this ball starts at the top of the incline. It has potential energy, but it starts off at rest. I guess it doesn't say that in the question, but it should say it starts off at rest. So we're going to say Ki is 0. Then it goes to the bottom of the incline here. So the final height will be 0, the bottom of the incline. So there's no UF there. And then something about rolling without slipping. When something rolls without slipping, there is forward and backwards work by friction. Those works cancel out, so there's no net work. This means work done by non-conservative forces. That's 0 when you're rolling without slipping because friction does no work. So we have potential energy going into rotational kinetic energy and linear kinetic energy. And there's the mathematical expressions for them. So potential energy is mgh. And then it's going to have rotational kinetic energy and linear kinetic energy. And I want to add those two together, the two kinetic energies, but right now they're not compatible, but I can make them compatible because I have I. So I can plug in I here. And this is rolls without slipping. For rolling without slipping, this condition is true. V is R omega. And I'm not going to replace V, I'm going to replace omega. So we're going to have omega here is going to be V over R. So there's the next step there, and I can cancel out some stuff. So I have a mass in every term. Over here for rotational kinetic, the radius cancels out. And now I have GH equals 1/2 times 2/3. So I have GH equals 1/3 V squared plus 1/2 V squared. So I have GH equals 1/3 plus 1/2 is 5/6. So I have GH equals 5/6 V squared. Now I can solve for V. And there's the final answer, square root of 6/5 GH. And that's when it converts potential energy into linear and kinetic rotational energy. That's the linear speed at the bottom. Now, if it didn't have that rotational kinetic energy, if it were just a conversion of potential to kinetic, if this were not rolling, if there was no friction on the incline and didn't roll at all, the answer would have been square root of 2 GH. And there should be a capital H over here, or lowercase h. So in that case, it would have gone faster. Now, part B asked, how would the answer change if the sphere were solid? So this is a hollow sphere. If it were solid, so let's go back to this step right here. We're converting potential to both types of kinetic. A solid sphere would have a smaller value of I, which conceptually means it's going to rotate easier. So without even looking at the math, conceptually the solid sphere rotates easier, so it's going to roll down faster. But if you have a hollow ball, a bigger portion of its kinetic energy has to be rotational, just because its moment of inertia is bigger. So if you had a smaller moment of inertia, you could have a bigger linear velocity. So that's the answer to part B. So that's our answer there. The solid sphere would be faster because it would have less moment of inertia. So its linear kinetic energy that it would gain would be greater, so it would go faster at the bottom of the incline. Okay, part C is the dynamics part. This is looking at determining an expression for the force of friction. And this is the type of question that doesn't really get changed up too much, so we'll go through and look at it. And this process is pretty much the same for a ball rolling uphill or going downhill, because in both cases you have friction acting to turn the ball downhill. All right, so I said this is a dynamics question. In AP Physics, when you have a dynamics question, you draw a picture, which we have, label the forces, then do F equals ma in the direction of motion. So picture, label the forces next. Those are the forces. Let's look at all three of them. So the first one is gravity. So mg, that's gravity. And we have two types of motion here. We have linear motion, so F equals ma, and rotational motion, so torque equals I alpha. And not all these forces apply to all these equations. So mg is going to apply to F equals ma. It has a component of its force that acts in the direction of linear motion, because motion is downhill, obviously. That's the direction of motion. So gravity doesn't act that way, but a component of it does. There's a component downhill, which is mg sine theta. But it doesn't apply any torque. That's going back to the cannonball question. When you have a weight, or when you have weight at all, when you have a force acting at the center of mass, there's no torque there. The next force is the normal force. So this is a force that doesn't really do much in the way of our problem. It's perpendicular to the direction of motion, so we're not going to use it there. And then it is parallel to the axis of rotation. So it's not going to cause any torque, so we're going to ignore, well, we're not going to ignore it, but we're not going to use it when we do F equals ma, torque equals I alpha. And then the force of friction. The force of friction is going to do a lot. It acts uphill, so that's against the direction of motion, so it's a negative linear force. And it applies a torque in the direction of motion. So this ball is rolling downhill. It's rolling downhill. So friction, which is acting tangent to the ball, so it is causing a torque, is going to turn it downhill. And it is turning downhill, so that's a positive torque. So now we can do F equals ma and torque equals I alpha. Okay, so you have F equals ma. We have two forces here. The force of friction is uphill, so it's negative. And then mg, only part of mg is downhill. So the component of mg downhill is this part right here, which is mg sine theta. So those are our forces, mg sine theta downhill and force of friction uphill. We'll leave that equation alone for now and go to torque. So we have torque equals I alpha. And here, as we said, we only have one force here, which is friction. It's a positive torque. FF is the force of friction. Torque is force times distance. We're going to do FF times R. And that equals I alpha. So for I, I plugged in 2/5 mr squared, or 2/3 mr squared. And then alpha, we're trying to unite these two equations. We have linear motion and rotational motion. So I'm going to convert alpha to A over R. And this is true. Alpha is A over R because it is rolling without slipping. And that is true when you're rolling without slipping. And I have the force of friction is 2/3 ma. So now these two equations are compatible. I can take this right here and substitute it in for friction on the force equation. And I get that. Now again, I can cancel out mass and then add this to both sides. And that's what we have there. Now I just multiply both sides by 3/5. So the acceleration is 3/5 g sine theta. And now I'm asking for the force of friction, so I can take this over here, plug it in for the acceleration, and get our final answer. So there it is plugged in, and then simplifying, the force of friction is 2/5 mg sine theta. Sometimes in physics C, you'll get to questions where it's not rolling without slipping completely. So here's three types of motion that basically a ball can do or a wheel. So the first one's pure rotation. That means the center of mass is basically at rest, and then all the points around it are moving in rotational motion, obviously, and that's just pure rotation. Pure translation means, well, nothing's rotating here. So in pure rotation, every point is going to have a different velocity on here in pure rotation. Pure translation, every single point on the ball or wheel has the same linear velocity in the direction of motion. So it doesn't matter where you are on the ball. If I could be here, it has the same velocity here, same linear velocity. Every single point has the same exact linear velocity. Where for pure rotation, every point was v equals r omega. And then translation and rotation, well, that's when you have both. And in this case, you have linear motion of the center of mass going forward. Then as you go out from the center of mass, you're going to get rotational motion. And it's more as you go outwards. So you're going to have going outwards v equals r omega, assuming that's rolling without slipping. So that's rolling motion. And a common physics C question is going from the transition from translation So we put a ball or a wheel on the ground and have it go forward with linear velocity. If there is friction, it's going to start rolling. So we're going to look at that transition between translation to rolling and then eventually rolling without slipping. Okay, here's a billiard ball. It's a solid ball, so I is 2 pi m r squared, has a mass m, radius r, and it's hit horizontally, along the line of the center of mass, so that it goes with an initial velocity that's just linear, initial velocity of v sub 0, and there's friction on the table. Due to the friction on the table, causing a force at the edge of the wheel, tangent to the wheel, or the ball, it's going to make it start to rotate. It's going to convert some of its linear velocity into angular velocity. So it's going to lose some of its linear velocity and gain angular velocity due to friction, because friction is going to do negative linear work and positive rotational work. So it's going to, after a while, its linear velocity is going to be a bit less, and it will gain rotational velocity. That's because of the force of friction. So force of friction acts tangent to the wheel, or to the ball at the bottom, and it's going to be a negative linear force, but then it's going to, if you look at the way the force is applied, cause it to rotate forward. So that's a positive torque. So it's a negative force and a positive torque. And we'll go ahead and do, again, F equals ma and torque equals I alpha. What we're trying to find is the time that it's going to be in this transition phase. That transition phase is when it's rolling and slipping. We want to find out how long it takes to roll without slipping. So we're going to do F equals ma, torque equals I alpha. We'll start with F equals ma. So the only force on it, like there's normal force and gravity, but those aren't in the direction of motion. The only force on it is going to be the force of friction. So F equals ma, which is negative force of friction. So this is a thing laying flat on a surface, so the force of friction is mu normal force is mg. So ma equals negative mu mg. The m's cancel out, and you get that a is negative mu g. Now what can we do with this to find time? So a lot of times when we're trying to do time, you want to do kinematics. So here is kinematics. So velocity equals initial velocity plus acceleration times time. Well, the initial velocity is given as v sub 0. The acceleration is negative mu g. So that's the expression for the velocity as a function of time. Now we're going to go over and go to torque and find omega as a function of time. So torque equals I alpha. Our positive torque is friction, so there's a radius r. So friction times r is a positive torque. Okay, and I can do a couple of things. I can cross out this r here with the r squared, and then the force of friction is still negative mu mg, so I'll plug that in. So there we go. Now the m's will cancel, and we'll get our expression for alpha. Okay. So that's the angular acceleration. Now that we have alpha, we can get an expression for angular velocity omega as a function of time. And then it starts off with linear motion. If it's in linear motion, there is no omega naught, there is no initial angular velocity, so that's 0. So we just bring this this alpha value in, and there's your omega of t. So it's just alpha times t, which is 5 mu g over 2r, and that's our omega function. So now we have two functions. We have the linear velocity as a function of time and the angular velocity as a function of time. And rolling without slipping is going to occur when v of t equals omega of t times r. So at time t equals 0, that condition is not met, obviously. So we'll go ahead and set this equation equals to this equation times r. That's what we have there. Obviously, r cancels out for the omega equation. Now we have that, we can just solve it. So I'll go ahead and add this thing to both sides, and then go ahead and solve for t. And that's the answer. So that's the time it takes from when it's first struck and has linear motion until it starts to roll without slipping. Okay, the last example here is about a rod that's pivoted at its left end, and it's allowed to drop, so it's going to rotate down like this. And there's two questions here. The first one is to find the initial angular acceleration. There was a typo, it said speed. Yeah, the initial speed is 0. And then part B says find the speed at the bottom of its rotation. So we'll go ahead and look at part A first. So it's asking for angular acceleration. That is Newton's second law for rotation, which is torque equals I alpha. So solving for alpha, alpha is torque over moment of inertia. So there's both things we need to find. The torque's the easier one to find, so we'll do that one first. So there's a torque on this rod because it's not pivoted at its center of mass. So its weight acts at the center of mass, so its weight is mg. And it acts halfway across the rod, so that's at L over 2. So our torque is force times distance, so it's mg times L over 2. And that's going to be over the moment of inertia. Now the moment of inertia for a rod pivoted on an end, it's a pretty common shape, so it's sort of known by most people. But we'll go ahead and derive it. So I is the integral. The integral here is the 0 to L, because you're going across the entire rod, you're pivoting at the left end, so you're going from the 0, the left end, to the right end, which is L, of x squared dm. Remember, a dm is a tiny piece of the rod. It has a thickness of dx. So dm is mass density, which is a linear rod, uniform. So it's m over L dx. So we have the integral 0 to L, m over L x squared dx. And I mean, that's an easy integral. So we have, I'll pull out m over L. Then we have x cubed over 3 evaluated from 0 to L. So parenthesis. And then when you solve that for I, you get ml squared over 3. So that's the moment of inertia. So now we can plug that back in to find alpha. So ml squared over 3. So you have alpha is the torque, mg times L over 2, over the moment of inertia, ml squared over 3. And the m would cancel, this L would cancel, and you would get, for the final answer, I'll write it down here, alpha is 3g over 2L. Okay, part B says find the angular speed of the rod at its lowest position. So that's here. So the rod's going to go that way. I guess that's not to scale. And it's going to have some angular velocity here. That's what we're solving for. It starts off from rest. And this is conservation of energy. So look at why that's conservation of energy. So we have ui plus ki equals uf plus kf. So I'll go ahead and define zero height is, let's just define zero height at the top. I could have defined zero height at the bottom as well, but I want to do it at the top. It doesn't matter as long as you're consistent here. So for this one, it starts off at zero height and it's not moving. So you have 0 equals uf plus kf. So let's look at uf here. Well, the actual thing falling, that we're looking at falling, is the center of mass. So the center of mass starts off here, and then it's up here. So it's below the 0 line by a value of L over 2. So our final potential energy is negative mg L over 2. And then kf, well, that's 1/2 I omega squared. And that omega is what we're solving for. So we're almost there. So next line we'll have mg L over 2. Move that over to the left side. Equals 1/2. So I, we know what I is. We just found it. It's ml squared over 3 times omega f. Now we just have to solve for omega f, which is a mess. So 1/2 cancels, n cancels, one of the l's cancel. Look at omega f is 3g over L square rooted. And that's the final answer there. All right, and that is more about angular energy or rotational energy. And that's it.